So when it comes to looking at sources of multicollinearity, then the main thing to bear in mind here is it's often to do with the limitations of the data set that you're actually able to collect. Okay, so necessarily in social sciences, the data that you're able to collect may be quite imperfect. So some examples of that might be the data collection method employed. So you might be only sampling over a limited range of values taken by the regressors in the population. This might be an especially acute problem if the size of the data set is small. You might also find that you've got constraints on the model or population. So the example that's discussed here is if you've got things like income and house size. These may naturally be interrelated. So if these are X variables in the model, it's natural to assume that income and house size may be interrelated and correlated, and therefore it might be difficult to isolate the impact of income or house size individually on the Y variable. And then the third example here, model specification. We saw an example of this in the second numerical example in lecture 3. If, for instance, you add polynomial terms to a model where the range of the X variables is small. This can also generate multicollinearity, and I think the main thing that you're really looking for in every example here is a high R squared value and low T value. Other sources of multicollinearity in finance and accounting problems include an overdetermined model. So you might have a lot of explanatory variables compared to the number of observations, or probably increasingly the case these days with more complex data, if you've got a large number of X variables in relation to the size of your sample. And precisely what is happening is that if you've got multicollinearity and interrelationship between the X variables, it's quite hard sometimes to isolate the effects of the individual X variables upon the Y variable in question, precisely because there's a lot going on. And I think you're likely to encounter this problem if you, for instance, do the statistical analysis of some survey data. It's quite common to have multicollinearity in this case. Now, another example, which I think is more linked to economics rather than accounting and finance. If you have variables such as consumption, income, wealth, population, etc., they may be correlated due to a dependence on general economic trends and cycles. So the classic example that I've seen of this is if you have time series in economics and finance that tend to show roughly exponential behaviour over time. That's precisely why in the earlier lecture exercise we adjusted for inflation when we're looking at the gold price and the stock price. So theoretical consequences of multicollinearity then. So I think this is inherently a practical problem due to the imperfections of any data set that you're able to collect. So it's not really a theoretical problem per se. So it says that multicollinearity is essentially a sampling phenomenon associated with the imperfections of each data set. It's always present to a greater or lesser extent. So the theoretical effects are in some sense muted. It's still potentially an important practical problem. So in the case of approximate multicollinearity, the usual regression estimators that are used in the computer software retain desirable theoretical properties. Things like they remain unbiased, so they will eventually get to the right underlying value as the sample size increases, and they might have properties like the best linear unbiased predictor. Okay, but I think really the main thing here with multicollinearity is that it is inherently a practical problem, okay, associated with the imperfections of any data set that you're likely to get your hands on. And really one of the main things to watch out for, and the examples we'll see in this lecture, is a high R squared value and low T values. In terms of the regression theory then, so if you look at the ordinary squares regression estimator beta hat, you have multicollinearity so that this matrix here, x transpose x, is not invertible, so the inverse doesn't exist. What happens is that the parameter estimates have infinitely variances and covariances. And again, multicollinearity is a practical problem, it's not really a theoretical thing. So in practical situations, you have only approximate multicollinearity. So in practice, you can actually, you may not be particularly trustworthy. So the things to sort of watch for here are things like, if you've got multicollinearity, you might have estimates with large estimated standard errors, and the parameter estimates may themselves be highly correlated. Now these are important because if you have correlated parameter estimates, this is suggestive of problems with numerical computational routines, and again this is a practical problem here, multicollinearity, and it is all to do with, can you be sure that you can trust the results of a computer generated regression output? Okay, your laptop is unlikely to explode, it's just you want to be sure that you can trust any computer generated output that your computer produces. Linearity is bad news for two main reasons then. So the first thing is you often have large estimated standard errors. So how this often manifests itself in practice is that you have high R-squared values and low t values. So when you have these large estimated standard errors, this does give you low t values and an inherent lack of precision associated with the parameter estimates. You get wider confidence intervals, and the large estimated standard errors may affect hypothesis tests precisely because if you increase the estimated standard error, you reduce the t values and you reduce the statistical significance. The second problem is that you might find correlated parameter estimates. This is another potential source of errors in a computational routine, and the reason this is such bad news is it's suggestive of numerical problems with the computer program. Okay, so again, you might be able to actually compute this thing and your laptop is unlikely to explode, thank goodness. Okay, it's just that you need to be aware that you might not be able to trust the computer generated output that you're able to obtain. Okay, look for these two things here with multicollinearity, large estimated standard errors, correlated parameter estimates. In my experience, you usually find high R-squared values and low t values. I just wanted to try and clarify then this effect of multicollinearity upon hypothesis tests. So what happens is it becomes harder to reject incorrect hypotheses, and there's an inherent loss of sensitivity. So for instance, if you test a null hypothesis that say beta 2 equals 0, so this would be a natural hypothesis test if you wanted to test for an effect that x2 has upon y. So if you use the t ratio, the t statistic would be the estimate divided by the estimated standard error. Then if you increase the estimated standard error, you decrease the t value and you decrease the p value that's calculated because of that. So the t ratio, it says there, reduces in size and its statistical significance becomes reduced. So the net result is that it becomes harder to reject incorrect hypotheses. So precisely because the estimated standard error increases, it becomes harder to detect whether or not there's a relationship between x2 in this case and y. Okay, precisely because multicollinearity can cause the estimated standard error to increase, and how this practically tends to manifest itself is that you often get a high R-squared value in your regression, but with low t values accompanying that value. To reinforce this then, so in terms of practical consequences of multicollinearity, it's almost like being a detective rather than a statistician. In practical problems, you need to look for something that does not look quite right, and I think this would be a very general skill as far as accounting and finance is concerned. And the crucial thing that I've learned as a applied statistician is you often see high R-squared values coupled with insignificant t ratios. So what you've got in this case is a contradiction, and always look for these sorts of contradictions whenever you're looking at any numerical or accounting and finance data. So you've got a contradiction then because the high R-squared values suggest that the model is good and explains a lot of the variation in y. T ratios are non-significant, suggests that the individual x variables do not affect y. Okay, so what is going on here is that you've potentially got quite a complex problem and interrelationships between the x variables, precisely this issue of multicollinearity. So it's obvious that there's some sort of relationship between the x values and the y values because the r squared value is high, but because the x variables themselves are interrelated, it's quite hard to isolate the impact of the individual x variables upon y. So you often get this contradiction then, r squared values, t values. So just to recap then, often you get high r squared values and low t values with multicollinearity. That's the thing I've spotted in practical problems, but there are a number of other ways in which this effect manifests itself. So you might get unusually large estimated standard errors. These then lead to these non-significant t ratios. Large estimated standard errors also result in wider confidence intervals, precisely because if you compute the confidence interval, you have something that's multiplied by the estimated standard error, and as the estimated standard error increases, the amount of error on either side of the estimate. Okay, so there's various different ways that this effect can manifest itself. Okay, the crucial thing though I think is this high r squared value coupled with low t values. Okay, and I think these are various things that are discussed in the textbook. We have quite a good choice of potential topics to look at, but I think really here the book missed a trick. The emphasis here, I think, if you've got a practical problem, is look for high r squared values and low t values for your indication of multicollinearity. Practical consequences of multicollinearity are then you're unlikely to blow up your laptop, but you have these potentially serious numerical instabilities. So you can still probably run the computer routine and get some sort of an answer, it's just you may not be able to trust the answer that the computer gives back to you. So what you might see then as evidence of the numerical instabilities, then you might get that parameter estimates and their associated estimated standard errors become very sensitive to small changes in the data. Look for things that look wrong or strange. Very useful thing to do whenever you're looking at any numerical or accounting and finance data. And as part of that here, what you might see is that regression coefficients take the wrong sign or otherwise look strange. It's possible that it's difficult to assess the individual contributions of the x variables to either the regressions from the squares or the r squared statistic. Again, this is just another way in which it's hard to isolate the impact of the individual x variables from the y variables, which I think in practical terms just repeats that you're likely to see high r squared values and low t values. And again, you might see that parameter estimates that you get from the regression model are highly correlated. This is often a indication that you've got some sort of numerical errors in your computational routine. So I want to try and give another illustrative example of multicollinearity. So we've got a slightly artificial example in this case, but we want to, in our example, try and explain expenditure in terms of income and wealth. Okay, and in this case, what you're going to find is that because income and wealth are highly correlated, highly interdependent, their interrelationship means it's hard to isolate the individual impact of income upon y and wealth upon y. Okay, and then as I keep trying to repeat here, okay, sometimes I think the textbook actually goes about this the wrong way. Really what you're looking for with a practical problem, high r squared value and low t value. And I suspect this is probably the single biggest indication of multicollinearity in any of the data examples that you're likely to see either on this module or in the course of doing your dissertation. Okay, so you know from the practical context here that income and wealth are likely to be interrelated, so you might find it difficult to isolate the individual impact of income and or wealth upon y, and you're likely to find once you press go on your computer high R squared values and low t values.